So, learning ranges, a paradigm shift. We'll talk a bit about why that's a paradigm shift as we go. Quick introduction, Anthony Nicholls. I'm a senior software developer at Focusrite. I've got about 8 years professional C++ experience now. So I was working at Sonox previous to this, most of the time predominantly using the Juice framework. Caveats though, I'm not an expert on the C++ ranges library. And I'm not a functional programming expert either. So this is really just a view on me trying to learn ranges, a bit of a story of me learning it and how it's changed some coding styles for me, but also some of the challenges. Quick guide to the slides. It would be helpful if you're able to take note of the slide numbers in the bottom right corner. So if you've got any questions at the end, it's just a little bit easier to guide back to them. And the slides, they will be available on this link. I haven't uploaded them yet, but I'll make sure they're uploaded before the end of the day. So you can access all of these again later if you need to. So let's jump in. First of all, we need to ask ourselves the question, what is a range? So I've defined a range to be an abstraction of something iterable. Often it's consisting of a begin and an end iterator. So we need to know what an iterator is. I've defined it as an object that can be used to transverse a range, giving access to a single element in the range at a time. So the question is, are there any ranges in C++ 17 and below? Does anyone know the answer? Or got any suggestions of things that would come under the definition of a range based on that previous definition? String view, yeah, string view would be a range. But thinking of some other things that you might be more familiar with, for example, containers, such as an array, list, map, vector, they all fall under this definition of a range. So part of the changes that have come in is to kind of redefine what already existed without actually making changes to it. So when I want to learn something new, I like to set myself some kind of task, and in this particular case, I think I wasn't really clear what task I wanted to set. So when I do that, I normally turn to something called Project Euler. If you're not familiar with it, I totally recommend checking it out. There's more than 760 mathematical problems to solve. You can use any programming language. I've seen people on there using things like Excel, assembly, all sorts. It's free. A login is required if you want to check your answers, or they could probably Google them, to be honest. And if you do have a login, then once you've solved the problem, you can also access a forum where you can see all the different solutions from different languages, etc., which can be quite an interesting insight just on its by itself. So I highly recommend Project Euler. So let's just look at problem 1. Really simple, right? Find the sum of all the multiples of 3 or 5 below 1,000. So let's look at this really naive solution. We start off, we have a variable sum. We're going to loop through all the numbers, 1 to 999, incrementing by 1 each time. Check if the I is a multiple of 3 or it's a multiple of 5, add it to the sum and return the sum. Okay, but how readable is this? It's not exactly the most readable code, even for something so simple. Just to quote Robert C. Martin, the author of Clean Code, it says, the ratio of time spent reading vs writing is well over 10 to 1. We are constantly reading old code as part of an effort to write new code. He goes on to say, there's no way to write code without reading it. So making it easy to read actually makes it easier to write. So let's try and embrace this. Let's look at this first. I describe this as being a multiple 3 or a multiple 5, but that's not quite what it says. So let's make it say something more like that. So here we are, is multiple of, or is multiple of. Or we could even just write another function that just says, is multiple 3 or 5. It's a bit more English. But you know, is that really the only improvement we can make to this? I mean, maybe we could change some variable names, but I'm thinking something more fundamental. Jules alluded to wanting to use, remove his for loops earlier. So let's look at range-based for loops, at least an improvement on the traditional for loop, or at least according to CPP reference, they say it's a more readable equivalent to the traditional for loop, operating over a range of values, such as all elements in a container. So note those words, range, in there, and such as all elements in the container being a range. So how can we, well, what would it look like first if we were to change this line of code? So it might look something like this, if we wanted to change it to be a range-based for loop. what might an implementation look like? Well, we talked about the use of containers, so let's just try it. So we could write a function called integers here. Takes our start and stop. We're going to create some vector that's going to be allocated the right amount of size in order to store all those numbers. We're going to use this algorithm called iota to fill the vector with all the numbers, and described here by CP reference, it fills the range with sequentially increasing values, starting with value and repeatedly evaluating plus plus value. That's exactly like our for loop, right? And then we can just return that vector. So now we've got this, it's working, and as a nice little bonus, we can also make our variable const. So we don't have it, it's no longer mutable. So we could say the code is arguably more readable, at least going by CPP reference. A mutable variable has been removed, but any keen-eyed C++ developers probably already spotted the issue. The code requires a vector to be created up front. So the time it's going to take to create that vector and the space that vector requires is going to be proportional to the length. So this is additional work that needs to be done before we even start iterating through the for loop. And this is what it means by a container to own the data it abstracts. So how can we get the benefits of the container without the cost? So this is where we introduce the idea of a view. So a view is a type of range. I think string view was mentioned earlier, but it's something that does not own the data it abstracts. So quite here it says the time it takes to construct, destruct, or copy a view shouldn't depend on the number of elements. The algorithm is required to be lazy evaluated. So what do we mean by lazy evaluation? To evaluate an expression at the point it is needed. So a good example of this is the traditional for loop. If we were to look at the traditional for loop, we assign some variable at the beginning. We then check some condition, run the body of the for loop. Straight after that, we increment it, and as soon as we've incremented it, check it again. And we keep going around unless we leave the body of the for loop, in which case we stop incrementing the number, or the condition no longer matches, and therefore we leave the loop. Okay, so going back to the code that we'd written, but we want to get rid of the vector now. We want to try and use a view. A good way to start to understand this is to maybe look at what the compiler does to this. So the compiler splits this out like this. This is what a range-based for loop basically looks like after the compiler's had its way with it. And the first line is that we're assigning from our integers, we're assigning to some variable range. But we don't want to do that with a vector anymore, so we're just going to make a class. And just for demonstration purposes, let's call this integer view. And once we've got that variable, range, it needs two member functions, begin and end. Mentioned earlier that normally a range is going to consist of a begin and end iterator. So let's just make a nested class iterator. So we've now got our integer view iterator. And then they need to be comparable. So let's add the equality comparison operator. And the iterator needs to be incrementable. So we need to do a pre-increment on it. So we add the operator for that. We need to be able to dereference it. And importantly, when we dereference it, it needs to return an integer. So we need one of those as well. And at that point, you've kind of got all the things you need. So let's just start filling this in. We've got our constructor, which took the two integers. Let's just store them as private member variables. We've got our two member functions, begin and end. They need to construct some iterator. Let's just pass one of those integers. So we've got the start and the stop. And the start's obviously going to represent the begin, and the stop's going to represent the end. So we store those in there. Then we've got to implement this equality comparison. And so we've got one integer inside of the iterator. So we just compare that integer. We need to do the pre-increment, so we pre-increment the integer, and we have to return a reference to ourselves. And then the dereference is just returning that integer. Believe it or not, that's it. That would be your integer view. That would get you the same benefits as we had before. So the code is arguably more readable. A mutable variable has been removed. And now the size of the object is just 2 ints, regardless of the length of the range. So the important thing here is the value is being evaluated lazily when it's required. It doesn't evaluate all of these values, even if it doesn't need them, like if we break out of the for loop, for example. So at this point, let's introduce the ranges library itself. So first of all, we have ranges in C++20 and some headers of interest. You shouldn't have to use these ones so much, but essentially, ranges is built out of concepts and iterators. That's the most important aspects to it. And they're the building blocks for what are called the views, as we're just looking at what a basic view was. Obviously, the views inside of the ranges library are a bit more comprehensive than what we just wrote. And there's a namespace, alias, stud views. It's provided as a shorthand for the stud ranges views. Sometimes this confuses people because they're including the ranges header, but then they're dealing with views, and I think this throws some people, so I thought it's worth putting in there. And then there's the algorithm header. So all of the algorithms in the algorithm header have been rangified, which means that they can take a range rather than a pair of iterators. So for example, let's say we make some array. If you're not familiar with this syntax, by the way, you don't have to declare the type and the size of the array as long as it can be deduced at compile time. And we might have sorted this like this previously, passing the beginning and the end. If you need a special type of sort, there's an additional argument as well. But the new one, we can just pass the range straight into sort. But note that this sort is in the ranges namespace. So you include algorithm, but algorithm has a namespace called ranges, which all of these algorithms are inside of. Some notable exceptions. There are some algorithms in numeric and memory. Unfortunately, these are not included as part of the C++20 standard. So Casey Carter said, every time someone asked me why we didn't cover numeric and memory algorithms, we thought 187 pages of technical specification was enough. So I think I'm kind of inclined to agree. I think it's good that at least they've got something in, and we've got something we can start working on. So if you really wanted, and you were stuck, and you were trying to use ranges, and you, let's say you wanted to use accumulate, which I'm going to need to use later in this talk, you could do something like this. It's not ideal, but you could do that until you have accumulate. Or better still, Tristan Brindle has made a header which has all of these numeric algorithms for C++20 ranges. So you could just go and borrow that and say thank you very much. Library support. So first of all, Visual Studio 2019 has now got full support for ranges, fantastic. GCC, as of version 10, full support, fantastic. Clang, version 13, still only partial support. I don't know what support it has exactly, but it's not full, so I'm not relying on it. And then Xcode, even as version 13, still no support whatsoever. So for my use cases, this means that I can't really use it in my work environment because we kind of rely on this. We need Xcode, we need to be able to run on macOS machines. But what you can do is you can go to this library called Range v3. So it's written by Eric Niebler, and this range library is for C++ 14, 17, and 20, and it is the basis of the code that went into C++ 20. It is the thing that built the technical specification for it. So it's very, very similar. If you want to adopt it and you're worried about using a whole load of extra ranges, like views, for example, that are in it that aren't available in C++ 20 because you want to move to C++ 20 later, you could do something like this. There's a namespace in there called CPP20, and that should limit you to only using the views that are available for C++ 20 should you then finally get the support. So let's talk about views a bit more. So there's two types of views. There's view factories. These are views that do not require some other range as an input. So note there's iota. That was an algorithm that was in the numeric header, but this isn't an algorithm, this is a view. But it does the same basic thing, and in fact, it's a direct replacement for the integer view we wrote earlier. So now we can just drop in views iota, and this will work just as it did before. The second type of views are view adapters. These are views that require another range as an input. So let's just take a look at a few of these, what I mean by that. So let's have a look at reverse. First of all, let's imagine we've got this line. So we've got iota, and it gives us the first three integers, so 1, 2, 3, nice and easy. Now, we could use reverse like this, so we can just pass the range into reverse, and we have like a functional style of composition, and then it would 3, 2, 1. But more commonly, you would probably want to use the pipe operator. And all this pipe operator does is things on the left of the pipe are going to be funneled through to the things on the right. So the reason you'd want to use this is that you're going to find you want to compose these with several different views all stringed together. And as you do that, if you were to continue to use the functional composition style, you're going to find it gets very, very nested, and you're going to feel very, very dirty. And if COVID doesn't make you clean your hands, then I hope this does. Yeah, stick with the pipe operator. View adapters, let's have another look at the other one. So this take takes the first n elements from some range. So we've got iota here, and it should give us 1 to 999. But we're just saying, hey, just take the first 3, and it returns 3 elements for us. Note, I said it returns 3 elements for us. That doesn't actually happen on this line of code. I'll try and go over that later, but nothing's actually happening here other than constructing an object. And in this instance, we could say, okay, well, we're going to take the first 3, and then we're going to reverse them. So we get 3, 2, 1. But if we were to flip that around, we could say, hey, reverse it, then take the first 3, and suddenly you'd have 999 down to 997. So I think it becomes very readable with these pipe operators. You can see step by step exactly what you're doing. So another really common view adapter is the filter. So let's imagine we've got some lambda here called isEven, just checking if something is a multiple of 2. And we're going to go through some iota that's going to give us the numbers 1 to 999, filter those that are even, and then take the first 3, and that's going to give us 2, 4, and 6. But again, if we were to flip the order of those, you'd take the first 3, so you'd have 1, 2, 3, and then filter it by those that are even. You're just going to be left with a range that is just one element that is the number 2. So the way to think about views is they're an abstraction layer over iterators. You should treat views much like you would an iterator. It's just my personal opinion and from my experience. But I would say that you should normally, they should normally be local, non-const variables created on the stack and passed around by value. I can see some use cases where you might have them as members, but I think most of the time you're probably just going to create them, use them, throw them away. Going back to this, if we look back at what we had in our for loop, we've just talked about filter. So we've got an if in here, we can just replace that with our filter. So no longer is the if statement in there, and suddenly we're just adding numbers together. Which, of course, is already an algorithm in numeric. So unfortunately not included part of C++20, but it's not too hard to write something that would at least give you the same functionality. And then we can just return accumulate. So that's really nice. It's a good start. Let's just look at this. So we've got auto here. I said about you just want to create them or throw them away. Note that it's non-const, and that's because it's going to hold some state. So when we use it in accumulate, that's going to iterate through that range, and it's going to change state in that view. So it's really important, just like your iterators, that it's not going to be something that's const. So I want to talk about higher order functions. And this for me is where the paradigm shift comes in as I started to use ranges. I found that there were things I wanted to do, that there were particular ways I would have done them previously, and I was struggling to figure out how to do them. And I think higher order functions is where this sort of, where it leads you eventually. So a higher order function, if you're not already aware, is a function that takes a function as a parameter, or it returns a function, or both. So here's an example of what I wanted. I didn't really want my is multiple of 3 or 5. It was a bit too specific, so I wanted something that was a little bit more readable. I wanted to write this. I wanted to write is multiple of 3 or is multiple of 5. I think it's still very readable, but also it's much more composable, We could change what that 3 and 5 is. We could have parameters coming in. So the first thing, how would we write the is multiple of? Well, we'd write a function. It's actually not too difficult. You take the argument, the multiple, and then it's going to return another function. In this case, the lambda, that's going to capture that multiple and create a function that's going to test whether some value, a parameter passed into the function, is a multiple of the multiple we just selected. Okay, so we've got that. But how would we do this or? In our previous slide, you can see that we had an auto return on is multiple of. It's quite difficult. So for the purposes of what I was doing, at least with Project Euler, I decided, hey, it'd be really neat. I want to do this in lots of places. I made a predicate. I didn't make it exactly like this, but just for demonstration purposes. It's a std function. It returns a ball. It takes an integer. It's a predicate. And all I have to really do is just change the return type of that is multiple of. That's fantastic. And then we need to be able to write an OR operator for the predicate. So we can just write this, and we can see that it takes 2 predicates and returns some other predicate. And in here, we're just returning another function, captures those 2 predicates, the left-hand side and the right-hand side, takes in a value to test, and then is going to return the result of calling the left-hand side or the right-hand side. And there we have it. We have a solution. And if we compare that to what we had in the first place, I think it offers for much more readable code. It's not necessarily the most intuitive the first time you do it, but I think it does offer something that can be more readable. So let's jump into another problem. So problem 2. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even valued terms. Okay, so this is one solution we might suddenly write out just to kind of get some ideas down on paper. So let's just loop through all the numbers, 1 to actually 3,909,999. Then filter those that are even, filter those that are Fibonacci, and accumulate them, right? That's basically what we had in the last one. Except when we get to this one, how would we implement is Fibonacci? I'm sure there's ways we could do it, but I wonder if there's better ways that we could achieve this. So let's just look at a typical recursive Fibonacci function. So this is what we normally think of when we're talking about Fibonacci, or at least very common. So how could we use something like this to achieve it? Well, we could first go in here, we could get our iota, and we see here that we're going from 1 to std unreachable sentinel. So the question is, what is a sentinel? I said earlier that that ranges normally consist of a begin and an end iterator. I was almost lying, because sometimes they replace the end iterator with something called a sentinel. A sentinel is essentially an object that can be used instead of an end iterator to determine the end of a range. So if we go back to our expanded range-based for loop, here's all of the examples of where the begin and the end iterators are used. If we look at where begin is used, we can see that it's used to test against end. It's used to, you need to increment it, and you need to dereference it. However, if we look at where the end iterator is used, it's purely used just to compare it with the begin in order to determine whether you have reached the end of some particular range. So essentially, a sentinel is kind of taking abuse of this. It's taken advantage of this and saying, well, what if we made a special type for the end, and in the case of unreachable, we could just say that it always returns true, that the condition has been met, and we just keep going through our loop forever and ever. And that is essentially what a sentinel is. I think understanding sentinel isn't super important to get using ranges, but it does give you a grasp of how these things are working. And for example, if you have a sentinel, you might not be able to determine how long some particular range is without iterating through every single element within it. If you've got an actual iterator, you've kind of got a begin and you've got an end, and you can look at the difference between the two and say, hey, that's the length of it. If you've got a begin iterator and you've got a sentinel, you might have to get all the way through until you hit that condition in order to figure out how long that particular range is. something to watch out for, because suddenly, if you're looking for the length of something, the performance might suddenly shoot up. Now we can use our transform to transform to Fibonacci numbers. So now we're transforming to each Fibonacci number. We're doing the first Fibonacci number, second Fibonacci number, so on and so on. We can filter those that are even, and then we can use something called take while. And this is another example of the higher order functions that I think makes this stuff a bit more readable. Most of the examples you'll read online will just put a lambda straight in here. I actually find it much nicer if you write that out with something named like this, so that it reads more human readable. So what would is less than return. Actually, first of all, the other thing to point out here is that this is going to be another sentinel, right? It's going to basically create one of these special end iterators, if you like, that it's going to use to determine once it's reached some particular point. And all that would look like is this. It's pretty simple again. Again, it's another function that returns a function. We take the limit, we capture it, and we return a lambda that returns the value, returns if the value is less than limit. Great, fantastic. We've got something, it's working, but it's still not really the best, because that Fibonacci function, as we iterate through this, which is all going to happen on this line, by the way, on this one single line as we return it, that Fibonacci function is going to go through and figure out all the Fibonacci numbers, all previous, every single one it goes through, it has to go back through and wind back again and again and again, which isn't ideal. So there's other ways we can do it. We can use generate. Now, this is something that's in the Range v3 library, isn't available in C+20 yet, but I'll show you a way to get it in there. So, yep, generate, and we're calling this make Fibonacci sequence. We'll go over in a minute. This is a bit ugly, but this is how, if you were doing C+20 a way, you could write something that does something a bit like the generate. I've tried to keep it simple for the slides. It is useful for these kind of things, but then again, it may not be the most useful thing to be using in everyday life in your code. But I wrote an example here. Originally, when I'd done this stuff in Project Euler, I was using Range v3. But if you wanted to move it over to C++20, then you could write something like this. Basically, it just infinitely goes through and calls our function. And in a generate, what happens is you pass a function in that every time it's called, it's going to return a new value, and that would be the next value within that range. So yeah, you can see here, this is going through the infinite loop, and then we're just going to transform it and say, hey, take that number, actually ignore it, and just return some other value. There might be a nicer way to achieve this, but it hopefully gets the message across of roughly what it does. Then we call this make Fibonacci sequence. So this is going to be calling some function that, again, is returning a function, and is going to be called repeatedly in order to generate the next number. So here's the actual lambda function. If we step through, we can see that first of all, we essentially say to lambda, hey, here's two member variables for you, one called current, one called next. I'm going to set both those to 1, first two numbers of the Fibonacci sequence. And note that it's a function that takes no parameters. So almost always when this happens, you're going to find that you'll probably need this to be mutable, which I'll get onto in a moment. But the first thing to point out here is it just says, hey, the result's going to be whatever the current value is. I'm just going to set this local variable result to the member variable current, and that's what I'm going to return at the end. And then in between those two, this is where we need the mutable keyword, because we're going to update those member variables, current and next. And so current's going to become next, and next is going to add the result onto it, and that should get you through the sequence. Important thing is I made this a function that returns a function, because the last thing you want to do is make one of these, if you want this Fibonacci sequence, you want to use it in lots of places. You wouldn't want to use this more than once because it's changing state with that mutable. So you're going to want to say, hey, I want to make a new Fibonacci sequence starting from the beginning each time. So that's why it's wrapped in a function. Okay, so there we go. We've got a solution. It's a pretty clean solution. It should run pretty fast. And I think it's fairly readable. Hey, generate a Fibonacci sequence, filter those that are even, and just keep giving me those until they're less than 4 million, or rather until they equal to or greater than 4 million, and then add them all together. So let's just look at one more. So problem 7. And I'll quickly run over this one. I won't go into too much detail. So by listing the first 6 prime numbers, 2, 3, 5, 7, 11, and 13, we can see that the 6th prime number is 13. So what is the 10,000th and first prime number? Normally, if I was looking at this, I'd be thinking, oh gosh, that's quite a lot of calculations I have to do. Well, it doesn't look too bad, actually. So we've got our iota, which has got this unreachable range again. But fortunately, we're going to make sure that we do have some end when we get there, which is going to happen in just a moment. Then we're going to filter by is prime. I'll leave it to the viewer to figure out how to go and write that. I think just for the purpose of just showing what this does, I think it's okay. And then we've got this drop, and that just says drop the first n elements. So it's going to drop the first 10,000 elements, and then we can just return the front of whatever that range is. And we've got the 10,000th and first prime. So I think it's pretty neat to be able to write that. But it's still worth pointing out that you'd have to, it really does have to go through all of those to figure out what the 10,000th and first prime is. It doesn't just immediately be able to jump to that point. Because it's going to need to run that filter and figure out, oh, wait a minute, is this a prime, is this not a prime? It's not going to know how many to go through until it gets there. Right, so let's quickly just go over issues. So there are some missing pieces, right? You know, I've mentioned a couple of times that things that maybe aren't in C++20 yet. So ranges is a huge addition to the library, but some useful features are not quite available in the STL yet. However, I don't think that should stop us from using any of the library. I've seen a lot of people complain about it online and say, oh no, it's not working, and it's not good enough, this is the bug. Well, I think there's still things you could use about it. You could certainly at least start to improve your for loops, if not get rid of them entirely. Some of the library implementations are not quite there yet, so I mentioned about Xcode. If that's the case for you, then C++20 might not be quite right for you at the moment. But you could at least consider using the Rangebased free library as an alternative. And there's ways you could use it that would probably integrate quite nicely over to C++20. I found it a pretty seamless experience, to be honest. There's CMake support, there's VC package, Conan, etc. It's a very good library. However, one thing I have found in general is debugging and profiling is, well, it's not the same, let's put it that way, as I've previously experienced. A lot of work gets carried out on a single line of code. So, you know, there's a lot happening. You pack up these ranges, you compose them all together, and then suddenly you run it all at once. And all this is happening on one line of code. That means that stepping through with a debugger isn't going to be particularly helpful because you're basically just going to get to that line and go, oh, yep, it ran that line. It can also be really difficult to profile. It's really difficult to see exactly what's taking all of the time. It's not always immediately obvious. And personally, with the Rangebased free library, I've experienced some really significant differences between release and debug builds, much more significant than I've ever seen in anything else. So it's definitely something to watch out for. Maybe improved tooling could help us in the future. I don't know. I think that's something that we should certainly look into because it is quite a paradigm shift in the way that we do things. But one thing you can do is lean on your tests, right? If you write lots of tests around these things, then you should be able to certify that they're doing the things that you want them to do. Ultimately, it's just a different way of working. I think it can produce some very readable results, but I should also warn that I found there's a certain friction to taking it up in the first place. It takes time to really think about the best way to do stuff, and that resistance can be met with, oh no, ranges isn't right for me. Actually, I think it can be, and I think we should probably all embrace it a bit more. So you can access these slides later, but some resources. First of all, I want to point out a couple of talks that are actually happening at ADC. So I think straight after this, Timur's doing a talk on using the C+ standard library for real-time audio. I don't know if he's going to bring up anything about ranges. I'd be interested because I can see some potential for using it for DSP. Other people have mentioned that to me. I haven't tried it yet. I'd be a little bit worried about not knowing what it's doing in certain places, but it would be interesting to see what Tim thinks of that. I noticed that Nick Thompson is doing a talk on why the future of audio is functional. I'd be intrigued to see that and see what he has to say. And also, I talked about leaning on your tests. We've got Joe Noel from Focusrite doing the talk on end-to-end testing of a juice desktop application. And Paul Chowner, Harry Morley, and myself are also doing an online workshop called Put It to the Test. That's on Friday, if anyone wants to join online. I think it starts at 2 o'clock. And then just some other videos. Again, you can access these online. Free Your Functions, I think, is fantastic, by the way, as is the functional design patterns. Will help you see these different ways of composing functions together if you're not very familiar with it. And I mentioned Tristan Brindle earlier. He's made that header. There's a talk from CPPCon 2020 where he talks about this. And also another one from Timur, just talking about the ways that C+20 changes the way we write code. Yeah, some links. Again, you can access it all online. And questions?
Thank you very much, Anthony. Questions? Range questions. We've got one here.
Thanks. It's not really a question, but as it looks really like C++20 with all these kind of joins what Rust has been trying to do with functional programming and stuff. One thing I noticed while trying both languages is that regarding I think it's on the 170 slide about the debugging. Even though a lot of work can be carried out in a single line of code, because we split every part into named functions, views, and ranges, from at least what I've tried and experienced, it prevents a lot of bugs. Even though when you really have a nasty bug in your single line, it tends to happen way less. If you really test your bricks, and if it has been tested well because it's part of a standard library and stuff like this, from my personal experience, it really tends to happen less than when we may think about when we're used to using loops and more traditional C++ range iterators and stuff like that. Yep. So that's a pros I'd add from my experience.
Yeah, I think I'd second that as well. You're absolutely right. It does tend to lead to less bugs. There's less bug code. I think the kind of things that I have experienced do happen is more on performance. So let's say you make a mistake. Instead of saying take while is less than 4 million, you said filter is less than 4 million. Now, you're still getting the same range in terms of the numbers there, but it's going to keep on going and just keep going through it, and it's not immediately obvious why that's happening. So I think to someone who's trying to learn it and trying to pick it up, it can be, sometimes there's some surprising behaviors and it's really difficult to pick up. But I do agree with you in general, yeah, it does lead to less buggy code. It's clearer to read, which means it's easier to spot the mistakes. So yeah, absolutely.
Yeah, the debugging thing is interesting. I'm sort of thinking about stuff that I've written and how it would look with this, and it does feel like you just know you're going to get to that line. You go, oh, I know that the third thing in this array has got a problem, and you know you're going to end up jumping between weird double underscored standard library code and back into your code and out. So yeah.
Yeah, and certainly when I've used the Eric Niebler's Range v3 and you're in the debug version, how deep the stack goes for some of that stuff is, especially once you've got a lot chained together, it's really quite, it's very hard to make any sense of.
Pretty hairy. Yeah, any more questions? One over here.
Thanks. Do ranges play well with const expr? Do you know?
That's a good question. I guess my experience is I can normally do const expr in a lot of places, particularly if I'm writing some kind of lambda or something in place. But I haven't stopped to check whether it's actually becoming const expr or it's just letting me write const expr. So a little bit hard to answer for certain. Yeah.
Okay, thanks.
Any more questions? Doesn't look like it. Okay, great. Thanks very much, Anthony.
Thank you very much.